We're in Rosen, section 8.2 on solving linear recurrence relations. Here we are discussing a non-homogeneous recurrence relation, and a linear non-homogeneous recurrence relation, constant coefficients, has this form. It looks exactly like a linear homogeneous recurrence relation with a function in n added onto it. And the recurrence relation that is everything but that f of n is known as the associated homogeneous recurrence relation. And you see that it is a homogeneous recurrence relation. Here's some examples. It's got a degree 1 type recurrence relation, but we have a 2 to the n as a particular portion or non-homogeneous portion. Here we have a degree 2 recurrence relation with a polynomial in n as the non-homogeneous portion. Here we have a polynomial in n times an exponential in n as the non-homogeneous portion. Here my non-homogeneous portion is n factorial, but each of these has an associated linear homogeneous recurrence relation as shown. Now, the proof is in the book of Theorem 5. It's quite elegant and accessible. I recommend you take a look at it. But what it says is that if you have a particular sequence that solves the particular, that is a particular solution of the non-homogeneous recurrence relation, then if we add that to any solution to the associated homogeneous recurrence relation, that will be the general solution to the non-homogeneous recurrence relation. So our activity will be involved with figuring out ANH and ANP and then combining them in some fashion, which I'll address on the next slide. Here's the procedure you want to keep in mind for solving linear non-homogeneous recurrence relations. First, we tackle the homogeneous recurrence relation, find the general homogeneous solution, and write it down. That's going to be the ANH. But we do not solve for the alphas at that step. We'll do it at the very end. Now we determine the particular solution by selecting the proper form. This will be ANP. And at this point, we will have some constants we want to solve for in this step. Third, now we add them. We get ANH plus ANP. And that we're done unless we have some initial conditions available, in which case we will finally solve for the alphas for the general homogeneous solution. All right, let's take a look at an example. I want to find all solutions to this recurrence relation. AN equals 3AN minus 1 plus 2N. And then we want to find the unique solution for A1 equals 3. So this all means what is the solutions without consideration of an initial condition, and then with A1 equal 3, we'll zoom in on that initial condition. The associated homogeneous recurrence relation is AN equal 3N minus 1, so the characteristic equation is R minus 3 equals 0, which means R equals 3. It's my characteristic root, and the associated homogeneous solution is alpha 3 to the n. But we don't solve for alphas yet. We do alpha yet. We do it at the last step. Now let's tackle the non-homogeneous portion. Fn is equal to 2 to the n. It's a polynomial of degree 1. And we might guess that a generic polynomial of degree 1 would be our particular solution. So we'll guess P sub n is Cn plus D, where we'll have to try to solve for C and D. And I'll just say ANP equals PN in this case. All right, we're going to substitute PN in for AN in our recurrence relation. So this is PN, AN becomes PN. This is P at n minus 1. And then we have Cn plus D equals 3 times Cn minus 1 plus D plus 2n. And now we want to bring everything over to one side of the equal sign and then pull all the factors of n together and all the constants together. That's what we have here. We have a polynomial in n where the coefficient of n is 2 plus 2c and the constant is 2d minus 3c. If that's going to be equal for all values of n, then the coefficients have to be 0. So we get 2 plus 2c equals 0 and 2d minus 3c equals 0. And if we solve for c in the first one, we get c is equal to negative 1. Substitute and solve for d in the second one, you get d equal to negative 3/2. And now I can write down my particular solution. ANP equals minus n minus 3/2. Now I go to step 3 and I combine them. ANP plus ANH is minus n minus 3/2 plus alpha 3 to the n. And I would be done unless I have an initial condition, which I do. And I have A1 is equal to 3. So n is equal to 1 in this case. So 3 equals negative 1 minus 3/2 plus 3 to the 1 times alpha. Solve for alpha to get alpha equal 11/6. And there is my unique closed form solution for this recurrence relation. Let's check it. For alpha 2, for a sub 2, a2 equals 3 times 3 plus 2 times 2 equals 13. And down here, a2 equals minus 2 minus 3/2 plus 11/6 times 3 squared. Take off that square, we get a 2 down here. And this is 33/2 minus 3/2. That becomes minus 4/2. We get 26/2 equals 13. All right, so that's an example of a linear non-homogeneous recurrence relation solution. I'm going to take a look at this master theorem here. Whenever we have an Fn that is a polynomial possibly multiplied by an exponential, then my solution will be a polynomial of the same degree multiplied by that same exponential. The exception is if this exponential is a root of the characteristic equation and that root has multiplicity m, we have to take that proposed solution and multiply it by n to the m. That's fairly straightforward, except you have to be careful when s equals 1, because if you don't see an exponential, you have an implied s equals 1. And then you have to be careful if your characteristic equation has a root of 1, in which case you need to go look at that second situation for your particular solution. We'll do an example of this in a separate video.